Why are VAE-generated outputs often blurry? Imagine watching a painting slowly come into focus. That's similar to what happens when a variational autoencoder tries to generate images. These models are fascinating tools in the world of artificial intelligence. They learn to create new data by compressing information into a smaller space and then reconstructing it. But why do the images they produce often look blurry or soft? Let's break it down. Variational autoencoders use a process called encoding, where they turn images into a compressed form in a space called the latent space. Then they decode that compressed data back into an image. The goal is to make the output look like the original. To do this, they use a loss function called mean squared error, which measures how close the generated image is to the real one. But here's the catch. This loss function tends to favor averaging pixel values. When it tries to minimize errors, it smooths out the details to reduce the differences. That smoothing causes images to look blurry because fine edges and textures get blended together. Another reason is how variational autoencoders balance their goals. They try to keep the latent space distribution close to a simple prior, usually a Gaussian distribution. This is called the evidence lower bound, or elbow. This balancing act limits how expressive the latent space can be. When the latent space is less flexible, the model struggles to capture tiny details, which makes the generated images appear less sharp. Researchers have come up with ways to improve this. One method is to use different loss functions that focus on perceptual quality, like the Learned Perceptual Image Patch Similarity, or LPIPS. This compares images based on how humans perceive differences, encouraging sharper outputs. Another approach is to incorporate adversarial training, like in generative adversarial networks, which push the model to produce more realistic and crisp images. Some models even train in the frequency domain, where high-frequency information like edges and textures are emphasized, helping to keep details sharp. In practical uses, combining variational autoencoders with other models like generative adversarial networks or diffusion models can lead to better results. For example, the stable diffusion model uses a VAE trained with additional perceptual and adversarial losses, resulting in clearer, more detailed images. This shows how different techniques can work together to overcome the blurriness issue. Understanding why variational autoencoders produce blurry images helps us see both their strengths and limitations. It highlights the importance of choosing the right loss functions and training strategies to get better quality outputs. Compared to other models like generative adversarial networks, which often produce sharper images, VAs are more stable but tend to sacrifice detail. Recognizing these differences is key when selecting the right tool for a specific task. From an ethical point of view, knowing the limitations of variational autoencoders is important. If they generate images that lack sharpness or realism, it can affect how much users trust AI-created content. Being transparent about these limitations helps set the right expectations and encourages responsible use of AI in creative fields. So, in the end, the blurriness of VAE images mainly comes down to the way they are trained and the loss functions they use. But ongoing research and new techniques are steadily making these models produce clearer, more detailed images.